All right. So like I said, we'll review from the test last week. We will have. I'm not going to go over the exact questions, but I'll go over the ways to solve them as we can, keep going. If you do have further questions about the test itself, please come talk to me. So one of the questions I was noticing people they were struggling with was also the questions we were talking about last time: how to measure current, how to measure voltage, how to measure resistance, all that kind of stuff. So when you're measuring current, what are the steps for that? Break the circuit, measure in series. Okay, measuring voltage, measure in parallel. You don't have to break the circuit. Measuring resistance, isolate and measure in series because it's going to be in series with the meter. All right. Some of the other questions that we had we're going to go through was an example, was number 36 and 37 on the test. If I can get those papers. Yeah, one was the troubleshooting and one was the potentiometer question. So in this configuration, what is this guy? It's a rheostat. All right. So the first set of questions that it gives us is when we have RAB at 50% is where we're going to solve this. So if we have that, what value resistance do we have between A and B? 5K. How much do we have between B and C? 0. Because it's in parallel with a short. Remember, a piece of wire has 0 ohms of resistance. Parallel with anything, it's going to be 0. So we have the things we're looking for was VR1, VAB, VBC, VA, VB, and VC. And our signal ground was given to us there. So first thing we need to do to solve this circuit is how much total resistance do we have in this circuit? So our R total is equal to R1 plus the RAB plus R3. Because again, this portion has been shorted out. So there is 0 ohms of resistance in that connection. So we have, come on, whatever. So we have the 1.1K, we have the 5K, and we have the 3.4K. That gives us a grand total of 9.5 kiloohms. Once we have that, we can go through and solve the rest of these really easy. So VR1, we can simply take the 1.1 kiloohms, divide it by our R total, multiply it by our voltage total. So we're just using voltage divider. And we end up with 2.316 volts. VAB, we can solve the exact same way. 5K divided by the 9.5K multiplied by 20, and that's going to give us 10.526 volts. So again, just using voltage divider. So like I said, the one on the test, it followed the exact same pattern, exact same questions. I just changed the values of the resistances on this one. Okay? VBC is how much? Huh? 0. Because we're in parallel with the short. VA, so remember we go from point A to ground, encompasses what? So it's the voltage across AB plus the voltage across BC plus the voltage of R3. Because we're going from here to here. So that gives us 7 point, wait a minute, how did I do here? Oh yeah. So 7.158 volts plus our 10.526 volts. And the way I got the 7.158 is I went through and found what our VR3 is. Because I started with 20, I've got 2.316 dropping there. I've got 10.5261 dropping there. Add those together, subtract them from our 20. So that's where the 7 comes from. So VAB ends up being 17.684 volts. Okay, VB, we're measuring from this point to here. So what's the voltage? VR3. That's all it passes through. There's 0 volts here. There's 0 volts across this guy. So 0 plus the 7.158. So in this case, both of these are equal. Because from those points, how we have them labeled, they are measuring the exact same point. Any questions about that? Okay. Then the next step was we want to take VAB and we want to set it equal to 100%. And then we wanted to know the R total and the current total. So in this instance, if we were to take VAB to 100%, how much resistance would we have there? 10K. So what would be our R total? So we just add them all together. So this would be 14.5K. I total, we take the 20 volts divided by the 14.5K, and that gives us 1.379 milliamps. Any questions with that? Does that make sense how we got there? Okay. And then the next question was when we had VAB equal to 0%. So our R total is going to change, and what are we taking away from it? 10K. We're taking away all of it because this is all of it's going to be shorted out. So we end up with just the 4.5K. Our current total is then going to be the 20 volts divided by this 4.5K, which gives us that value. Yes?
So in the diagram itself, what is the physical difference between the rheostat and potentiometer?
The difference is, when we're physically looking at it, is the potentiometer has the 3 legs. We have, our circuit's going to look like this.
Okay.
This is R1, this is R3. When we have it connected as a rheostat, those 2 pins are connected together, or, yeah. So B and C are shorted together, or just literally we just take off the wiper and one of the outside pins. We don't have to short it out, but it's gonna act the exact same way either way. You just would draw it this way, connected into the middle pin, with this left pin not being connected to anything. The biggest difference here is this is what you guys should be seeing. Is before, when we had it connected as a potentiometer, no matter how we adjusted that guy, it was always going to give you the same amount of current. But now, when we have it connected as a rheostat or just a variable resistor, we're going to be changing our total current. So this could be used for like a speed control device. As we increase the potentiometer, increase our knob, we're going to decrease the resistance, which is going to change the speed of it. Versus just, it's a current-driven device versus a voltage-driven device. Make sense? Okay. The next question, a lot of people struggled on. The troubleshooting. Those kind of questions are not going away, just fair warning. This one was nice because it gave you information that you didn't necessarily have to calculate yourself. So in this equation, we're going to have 30 volts. R1 is going to be 3.2K. R2 is going to be 1.1K. And R3 was 1.1K. Our R total was equal to 5.4 kiloohms. Now, what we were given was a chart. So we have R1, R2, R3, and our R total. This one gave us the good, and then malfunction 1, and malfunction 2. So we had here just a bunch of measurements. So the nice thing is this one already gave us what these voltages are supposed to be. In future ones, that may not be the case. We may have to determine which one is what is good, out of the options. It may not label it as good. Okay? So in this case, we're told that we have 17.778 volts across R1. We have 4.074 volts across R2. And we have 4.074 volts across R3 with a total of 30.01 volts. Do you guys agree with that? Do those numbers make sense? Okay, you can go through, you can double check them. So the first one we were given is these are the measurements they got. So they got 22.326 volts, 0 volts, 7.674 volts, and 30.01 volts. And basically our choices are R1, R2, R3 is open or short. So we have to pick one of these options and determine. So looking at that data, what do we think happened here? We lost R2. How? It shorted out. Because there is 0 voltage drop across it. Because remember, a piece of wire has essentially no resistance, there's going to be no voltage drop across it. So yeah, we could say in here, with everything else being the same, with R2 being taken out of the equation, we could run through and recalculate this. Okay? Assume R2 is shorted. So now our R total changes to be 4.3. And then we could go through and use our voltage divider. So we take the 3.2K divided by the 4.3K, multiplied it by 30 volts. We're going to get the 22.326 volts. So a lot of it is remembering what we talk about and thinking about it, okay? So let's say I wasn't quite sure which one was going on. Practice it. Solve the circuit with that equation. So let's say if I wanted R1 to be shorted, okay? I figure out what is my circuit going to do, and can I duplicate those measurements? So in this case, you wouldn't get the 22 volts across R1 if R1 was shorted out because its voltage would be 0. Okay, what about R2 being open? What would happen if R2 was open? Yeah, they would all be 0, except for the one that was open. Because there's no current path, so there's going to be no voltage drops. So when you measure across the open, your meter then connects the circuit, and it gets the current that flows through it that direction, but it's going to drop all the voltage at that point. Because remember, how much resistance is your meter? Roughly 10 meg. Should be greater than 10 meg. It wasn't micro-ohms. You want your current meter to be micro-ohms.
I mean, maximally close. There's an image ball.
Yes, there is that. But, so remember, if you have 10 meg and you put it in across this guy, an open, basically now you've completed your circuit with 10 meg of resistance, compared to the 3.2 and the 1.1K, yeah, it may not quite be 30 volts. It's going to be 29.98 volts. The majority of it's going to drop across there. So either way, all you're doing is you're swapping out that resistor in for your 10 meg. Okay? So now the last question is, we get 30.02 volts. We have 0 volts, and our total we're reading. So what's that case? R1 is open. So in this one, R2 is short. And in this one, R1 is open. So like I said, a lot of these times on these troubleshooting questions, they're not going to be nice and spell out, this is the good value. This is the malfunction. One of the tests you're going to get is you're going to have 4 instances, 4 test cases, or 4 student circuits. Okay? This is something that I get to deal with all the time. I'm always dealing with these troubleshooting problems. Which student has it hooked up right? Which student has things open? Which things have them shorted out? It happens. That's part of this program, is we want you guys to learn these troubleshooting techniques. So we may give you this chart, but we're not going to label which ones are which. You have to figure out all the possibilities that are listed. So the first thing to do when you get this style of a problem is calculate it and find out what should the good values be. Based on everything that we've been doing, everything that we've been learning, what are the values supposed to be? And then start looking for the patterns. Do we have voltages that are suddenly dropped out? Do we have voltages that are taking everything? You know, it could be a combination. So take, as we go through these, apply the principles that we're learning and slowly dissect the circuit. What happens if I short this component? What happens to my circuit? Things like that. Yes?
Is there a way that we can review the questions that we missed? I have it pulled up. Yeah, it's not open until tomorrow.
Okay, yeah, you can, after tomorrow, you can review those questions. Do keep those amongst yourselves, just for now. So any questions about the troubleshooting? Okay, so like I said, these were the biggest questions that I saw most people miss. For the most part, there was some hit or miss here or through there, about the multiplication, division of fractions and monomials, that kind of stuff. But honestly, nothing I was too worried about. These were the biggest ones that I saw. So, any questions before we move on from there? Okay. So just so you guys are aware today, class is going to be a little bit different. We are going to be getting out of here a little early, probably about 2:40. I've got an appointment that I got to get to at 2:45, so we'll be cutting it close. But if you do need help, I will be back on campus about 3:45, 4 o'clock. So text me, call me if you have questions, if you need to meet me, whatnot. But I'll be in my office about after that point. I'll come back for another hour or so. Tomorrow, how things are going to work is I have another appointment that I have to get to. So I will be leaving lab tomorrow about 9 o'clock. So you guys will kind of be on your own for a few hours. I will not be able to return until theory. So I've let Adam know. So if you guys do need parts or whatnot, you can ask him for that kind of stuff. If you have questions specifically for the lab, ask them amongst yourselves. You can ask some of the third semester students if you need help. Also, I will have my phone on. I can also, boot up a Zoom call, things like that if needed to. Have you guys used Zoom before or not? Okay. But what I'll do is, for those of you who have or haven't, I will send out an email tonight with a link on there. So basically, you just click on that link, and it'll log you in. You don't have to have a Zoom account or anything installed on your phone or computer or whatnot. I'll try and have that open. I will try and talk to them and see if they can get me off to the room off to the side where I'm by myself, so I can have my computer open more and being able to talk to people without freaking everybody else out there while I'm talking and spewing to my computer when everybody else is kind of laying there. I have to go get an infusion. So basically I sit there with an IV in my arm for 3 hours waiting for them to get this thing finished. So it sucks and I have to do it. I try to get them scheduled so they don't interfere with classes. This was the only time they had, so I apologize for that. But just so you're aware, you can still get a hold of me. You can still call. You can still text as needed. But just so you know, just keep working on your labs, get everything done. That kind of stuff. If you do have questions, like I said, feel free to call, text. You can ask some of the other students. You can ask Tim to some extent, but you use each other. Use me as your first lines of resources first. Fair enough? And like I said, and then I'll be back in time for theory afterwards. So I'll get finished about 12:30 and then be back on campus. So that's how tomorrow's going to go. Like I said, I do apologize for that. I tried to avoid that stuff. So, oops, that was supposed to go in my last notebook. Let's start in with, there we go, I want that one. Series parallel circuits. So now we're going to take the two methods that we have learned about, series circuits and parallel circuits, and we're going to start intermixing and meshing these two guys together. So the biggest thing is we have to look at, when I'm looking at this circuit, what's in series, what's in parallel? How do I combine these together to find these answers? So some of the first things we're going to go through is terminology with our rules. So we've got, so the parameters we're looking at, we've got voltage, current, power, resistance, and then specifically current paths. And we're going to look at series versus parallel. So when we're looking at these guys, what are our rules with voltage in a series circuit? Voltage drops add up. So our V total is equal to VR1 plus VR2, so on and so forth. What's our rule for parallel for voltage? It remains constant. So our voltage is equal to VR1, which is equal to VR2, and equal to so on and so forth. Okay, what about current? It remains constant in series. Okay, Carson, current and parallel. It adds among the branches. So our I total is equal to the I branch 1 plus I branch 2, so on and so forth. Okay? Zach, what about power for a series circuit? Power adds up. Okay, Reed, what about power in a parallel circuit? It also adds up. Okay, Kately, resistance in series circuit. It adds up. Jeff, resistance in parallel. It adds up. Does it? Inversely, the conductance adds up. And so conductance is given with the letter G. So our R total is equal to, it's measured in S, Siemens. I don't disagree. So we use the reciprocal method. So the conductances add together, and then once we get the conductance together, we have to take the reciprocal of that to give us in resistance. Okay, and then the last one we have, Morgan, for current paths in a series circuit. How many do we have? What do we have? We have one current path. And Jessica, how many current paths do we have in parallel? As many branches as we have, so multiple current paths. So one of the reasons I want to go through this is this kind of separates and splits out all the different rules that we're going to be using. And we're going to be combining these guys together. So when we're looking at the whole circuit together, it's not going to fall into one of these realms. But bits and pieces of it are going to combine together in different ways. So remember these rules. Voltages for series, they add together to form the voltage total. In parallel, the voltage drop of the parallel components stays the same. In current, the current is constant in a series circuit. In a parallel circuit, each individual branch current adds up to the total current. For power, they both add together. For resistance, in a series circuit, we just add the resistance together. In a parallel circuit, we add the conductance together. We also use the reciprocal method. And we also have those couple of other ones that we talked about, the special case scenarios. If we have two resistors, or if we have the same valued resistors. And then the current paths, we have one current path in a series circuit, and we have multiple current paths in a parallel circuit, depending on how many branches we have. Make sense? Now you guys have those in your notes forever. You can always refer to them if you ever get lost solving these guys. Okay, some of the things we're going to talk about later on this week. We have what's called circuit loading. So what this is, it's the effect on a circuit when an element, and I use that term just very, very loosely, when something draws current from output terminals. So basically, circuit loading is defined as it's the effect on a circuit when we start using part of the circuit as an output. So for example, if we built just a simple voltage divider, let's say we put this in as a variable resistor. Okay? So if we have it set up like this, so we use our variable resistor, a rheostat, to control how much voltage drop we have. As soon as we connect something up here, like our fan, that fan is going to interact with the circuit. So if it has really, really low resistance, it's going to completely negate that resistor. And so our speed control is going to have a lot more of an effect on it as we adjust it. If this resistance is very, very large, our speed control isn't going to have that great of an effect on it. So it's all proportional to what are we connecting into the circuit after we've designed it. So we can design a circuit for unloaded conditions all day long, but until we load it, we can't calculate what's going to happen. Because like I said, with this guy in parallel with whatever the value is, it's going to have some effect on what this total value is. Kind of the idea with putting our voltmeter across these guys. If we have a good voltmeter that's greater than 10K ohms, we put it across this guy. So if we have 100 ohms here and we have 10K, what's that parallel equivalent?
ohms.
99 ohms? How many decimal points? Okay. If we have a crappy meter, sorry, this should be 10 meg or whatever, 10 meg. But let's say we have a crappy voltmeter and we only have 1,000 ohms across that. What does this value change to? Huh? 90.9? So yeah, so if we have 10 meg and across 100 ohm, we get 99 ohms. If we have a 1K resistor, we get 90. Those 9 ohms can be a big difference depending on how, what our total resistance is. If this guy is a 0 to, let's say, 50 ohm resistor, and we're just slightly adjusting this guy, that 9 ohms, it's already double, or it's already about 10% what that is. So right there, there's our margin of error just gone out the window. Just because we changed that resistor by 10 ohms, we've already thrown our resistance out the window. So this is why we have to be conscious of what's the final product that's going to be connected to our circuit, and we have to take that into account. Otherwise, we're going to load down the circuit. Make sense? Like I said, we'll talk about more about this when we get into some voltage dividers and bipolar voltage dividers, because that's going to have an effect on things. All the time. And we actually design them to be bipolar. The next one we're going to talk about this week is bleeder current. And that's actually kind of funny. I switched to red. That's really funny. So the bleeder current is defined as current that's left over that does not go through the load. Now, later in the week, this is when we'll be talking specifically about bleeder current. But I'm going to just introduce all this terminology up front. So the bleeder current is current left over that does not go through the load. We still have to have it, it's just not being used for anything. And then the last one we have is the load current. This is current that goes through the load. So bleeder current, stuff that doesn't go through the load. Load current that does go through it. And like I said, we'll talk about those when we get into these voltage dividers.
So is like the load, like considered a fan?
Mm-hmm.
Okay, so that would be like, so it's of course like the fan's not gonna take all of the current, so it'll like take some of the other current going through like that other like resistor.
Yes.
Okay.
So in this case, yeah, just like what he's saying, we're going to have current flow here. This is load current.
The other current, so that takes more. And then
This up here is total current. And this guy that comes up through here is bleeder. So we just have fancy names for everything so we can differentiate what's what. All right, so as far as terminology goes, that's really all we're going to be talking about. In the quizzes, there will be terminology brought back from previous sections as well, so pay attention to those. But as usual, let's start in with some of the math needed before we get into solving circuits. I know which is everybody's favorite. I apologize for reaching into the deep, dark depths of your minds and dragging stuff up, kicking and screaming. I had a lot of the same questions you guys posed in your muddiest moments. You know, when am I ever going to use this crap again in electronics? You have arrived at that day. The rest of the world is not going to use what you guys learned in high school. That's why we get paid the big bucks to solve these questions, because we understand this math and we use it. It's true. Yeah, or win random trivia. That's what you need them for. All right, so basically what we're going to talk about is linear equations. So linear equations are ones that we can graph. You know, they're going to progress one way or another. We can talk about quadratics, things like that. They're all linear because they can all be made by, you know, one fluid motion. So whether they go this direction, we don't actually have to lift our pen. We have the parabolas. We can make them that way. The problem is when we start getting into nonlinear, is you guys will start dealing in calculus, is you're going to start seeing problems that look like this. Another one you guys are going to see, you're going to see graphs that look like this, and graphs that looks like this. So these are nonlinear. These, yeah, line test is one of those. But even then, a linear equation, you could get that. That's still linear because it's still there's another name in there. It's not a function. That's the function test. Yeah. Like I said, there's a bunch of little things, but this is all linear because we can make the representative graph just by drawing a single line without having to move our pencil from the paper to a separate spot. So this is what we're going to be talking about, not these guys. You guys will get those in third semester. So basically what we have is we have a combination of systems. So we have y is equal to 6 minus x, where x is equal to negative 3. How do we solve this? Plug in the x for this right here. So we have y, 6 minus a negative 3. Two negatives becomes a positive. Okay. How about y is equal to 2x plus 9, where x equals 2 pi? Four pi plus 9. Now, pi is an acceptable answer. There are times when we want a specific value. That's when we would plug in 3.1415, or we would just plug in the pi value on our calculator.
We use pi a lot in this.
We will use it a ton. The last part of DC and then the first part of AC, that's all we're talking about is circles and pi. Because that's frequencies, that's how AC is generated. AC, you can think of it generated as a wheel turns, as a generator turns.
That's why it goes
Yep. Again, as I say, this is where all the stuff that you're like, I'm dragging out of your memory banks. And then also, yes, we will get into logs and natural logs too. Trust me, once you see how we use them, it'll make sense as to why we actually need them. Logs serve a very, very, very specific purpose in electronics. Okay. Do what? Yeah. Now it will have a use. That's the thing too, is the stuff that I'm teaching you, I'm not just trying to teach you because I want to, I need to fill time. This is stuff that we're actually, I wish it was just busy work. But in this case, these are actually concepts that we're going to be able to need and use. You may not realize them. We're not going to say, okay, now we're dealing with linear functions. It's just to get to the answer, you have to apply, a value that we calculated from here, a value we calculated from here, combine them together. When we get into the universal shunt meters is one, where we're going to be playing with these a lot. So another example, y is equal to x squared plus 2x plus 5, where x equals 6. We can plug this guy in. So what does our new formula become? (36 plus 12 plus 5) comes out to be 53. And then the other one we have to worry about is when we have them on opposite sides. So we've got negative 2x plus 3 is equal to 14x minus 5. We need to be able to solve for this unknown value. Add 2x to both sides. Add 5 to both sides. So this is going to cancel over here. These guys are going to cancel. So we're left with 8 is equal to 16x. Hey, look, we're reducing fractions, which is what we were doing the last week. Dun, dun. I wish I would have had that on my phone pre-recorded. Dun, dun, dun. So this is all the concept of linear equations. Even in these ones, all we're trying to do is solve for one of the unknowns. We get it down to the point where we have one of our unknowns, we transfer it and substitute it back into another formula to be able to solve for our final answer, in this case, y. Same with all these equations. All we're doing is trying to solve for the answer of what is y based on another variable. We're going to have a lot of equations that look more like this. We're going to end up with two equations on two different sides of the equal sign. We have to be able to mix and match and combine these guys together. So remember, on on these guys, when we're moving them across the equal sign, you have to do the opposite sign, opposite function of what's going on. So if we add on one side, we subtract to get it to the across the equal sign. If we multiply, we divide. And if we divide, we multiply. So we're moving across the equal sign, just like with the exponents in our fractions. When we move up and down across the fraction line, we take the reciprocal of that, of the power. So if it's x to the third and we want to move it below the fraction line, it becomes x to the negative third. Same thing with here. We're just treating the opposites as we go. Any questions with linear equations? This is really about, as deep as we're going to get into is solve for the value. Is that okay? Let's see. This one looks like tears. So multiplication of polynomials. Lots of big words. What is polynomials? More nomials. More than one numbers in a term. Okay? So in this case, yes. Biza specifically has only two. A polynomial can be anything greater than 2. So we got x plus 5, which now we have a binomial multiplied by 2x. So the reason we go through these is because, like I said, when we get into some of the more complex electronics questions, we're going to have variables and formulas all multiplied together, and we have to make sure we cover all the possible permutations of this. You guys remember FOIL? First, inside, outside, last. It's basically just a double check to make sure you have two binomials multiplied together, you get all the terms. Whatever method you guys want to use is fine with me. I don't have a preference. I will use FOIL. I'll just simplify these things down. My wife has been going through a bunch of stuff. She got her teaching degree and had to learn all the different ways to teach, which is what Common Core is becoming. Like, instead of you teach multiple ways to get to the answer, and then you can choose the one you like. And she talked about some of those, and I didn't like 90% of what they said. I thought, I'm just going to go back to the way it was taught when math was math. And she did not like that answer very much, but which I get. Some people learn math differently. I get that. But yeah, you make it. Yeah, I had a problem with some of the things that was I just couldn't wrap my head around it. But when we're doing this, we want to make sure we multiply everything across. So we take our first term, which is x, and we multiply it by everything in the second term. So we end up with a 2x squared, and then there's nothing else, so then we take our second term, and we go a plus 5 multiplied by a 2x. That gives us a plus 10x. And all the terms are accounted for. One of the things you'll notice too is we're going through when we are simplifying. This is how I will group my terms. So if I have things that are an x, everything is going to be labeled with an x with a single underline. X squared, I'm going to go through with double underlines. It's just a notation I learned when I was going through school. I don't even remember when, just to make sure I remember to group everything and not leave anything out. So if you see me putting weird symbols like that underneath them, that's just because I'm grouping things. That was right after the pterodactyls. They died off before I could go to school. My parents had pterodactyls. So we've got 2x plus 6 multiplied by 2x minus 7. So now this is when we would use our FOIL method. So we would multiply the first terms together. So 2x times 2x, 4x squared. The inner terms, so we got 6x and 2x. So that gives us plus 12x. See, first inner outside. Then we're going to multiply these guys. So we have 2x and a negative 7. And then the last one to do the 6 and the minus 7, which gives us a negative, I almost wrote 36 for some reason, not 6. So now we go through, we got to combine all of our terms together. So this is where I was saying with my grouping. So I have to combine all my x squared terms together. I have to combine all my x terms together. And I have to confirm basically my constants, my numbers. So we end up with 4x squared minus 2x minus 42. And we're going to be doing a lot of these things where just in the formulas we create, we're going to be multiplying values back and forth, left and right. And we're trying to get it down to where we can isolate these terms. A lot of times we'll be going from this method back into these guys. Because we need to, because then at that point we can factor things out. And then when we factor them, things start to fall away. Yes, third semester. We won't be getting into any of that stuff. Derivatives and integrals is what we'll be starting with in third semester. Yep. And one's making it bigger, one's making it smaller. Okay. Any questions about this? Like I said, this just takes practice to get used to again. Kind of the fundamentals. Everything that we've done so far, we're still applying. We're just making it more complicated. So before we were just multiplying, powers together, multiplying numbers together, finding factors, that kind of stuff. This is all we're doing. We're just making it more complicated because we're getting into these types of problems. Okay, let's do this. How about we give you guys a break right now, and then that way we can go until about 20 till, and then I'll let you guys leave. And we'll start right here because the next section is going to be a lot more fun. I need to find something that better represents tiers. So.